which of LL1, SLR1 and LR1 parsers can parse strings in the following grammar? In this question, a grammar is given to find which of the given parsers LL1, SLR1 and LR1 can parse the strings from the given grammar. So if we observe the grammar, there are two derivation trees for the terminal C. That is, from E we can go to B, from B we can derive C. So this is one parse tree. From E we can take this production, from E to E derives A, and from A can derive C. So there are two derivation trees for a particular string. That means the given grammar is ambiguous, and we know that we cannot parse ambiguous grammar by any of LL1, SLR1 and LR1. Cannot construct LL1, SLR1 and LR1 parsers for an ambiguous grammar. There is only one parser, which is called operator precedence parser, which can parse some of the ambiguous grammar. And if it is to be parsed by operator precedence grammar, that grammar should be operator grammar. Then only it can parse ambiguous or unambiguous grammars. So here, as the grammar is ambiguous, we cannot construct LL1, SLR1 and LR1 parsers. So here correct option is option D.
For four processes A, B, C, D arrived into ready queue at time 0 in the order A, B, C, D. The burst times of the process are 4 milliseconds, 2 milliseconds, 1 millisecond and 2 milliseconds respectively. Round robin technique is used with a time slice of 1 millisecond. If the context switches take 2 nanoseconds, then what will be the total time taken for all the context switches to finish the process's execution? Here, four processes A, B, C, D are arrived into the ready queue at time 0 in the order A, B, C, D, and the burst times for four processes A, B, C, D are given as: for A, it is 4 milliseconds, for B, 2 milliseconds, for C, 1 millisecond, and for D, 2 milliseconds. And the time slice is given as 1 millisecond. And time taken to switch from one process to another process after the time slice is given as 2 nanoseconds. Here round robin schedule is used to schedule the given process. So here the question is, we have to find the total time taken by context switches if we use round robin schedule. So in order to solve this problem, we have to write the Gantt chart. And if we write the Gantt chart, here it is at time 0, all the processes A, B, C, D have arrived in the order A, B, C, D. So let us allocate process A to the processor, that is 0 to 1, as the time slice is 1. After 1 millisecond, here process A will be preempted, and the processor is allocated to the next process. So here burst time of process A is 4 millisecond. As we have executed one time unit, 3 milliseconds is remaining for A, and next process B will be allocated, and it will execute up to 2 milliseconds, and the remaining time of process B would be 1 millisecond, and after that C will be executed after the time slice of 1 millisecond, and it will continue up to 3, and as burst time of process C is 1 millisecond, it will be completed. and after that D will be allocated. If you allocate, and it will continue up to 4 milliseconds. Here C is over, and the remaining burst time for D would be 1 millisecond. Now again A will be allocated. So here A up to 5, and it will be 2 milliseconds. And after that B will be allocated. It will continue up to 6, and process B will be finished. And later D will be allocated. Process C is already completed, so the processor will be allocated to process D, and it will continue up to 7 milliseconds. Now D will be completed. After that again A will be allocated, and it will continue up to 8. After that also it will be preempted after the time slice. As there are no processors, processor is given again back to A, so it will continue up to 8. Total here we have 1, 2, 3, 4, 5, 6, 7 and 8 context switches. So total context switches are 8, and time taken for one context switch is given as 2 nanoseconds. So total time for context switches is equal to 8 into 2, which is 16 nanoseconds. So here correct option is option D.
Find the number of elements in the power set of the set 1, 2, 3, 4, 5 containing 2 and 5. Here power set is nothing but set of all the subsets. Here we have to find the subsets containing the elements 2 and 5. So let us include the elements which are to be present. So here include 2 and 5, and for all the remaining elements there are 2 chances. That means they may or may not present. So the total subsets containing 2 and 5 would be, for element 1 there are 2 chances, for element 3 there are 2 chances, and for element 4 there are 2 chances. So the subsets which contain 2 and 5 are 2 into 2 into 2, which is 8. So here correct option is option D.
1 kilometer long 10 Mbps token ring has a propagation speed of 200 meters per microsecond. 50 stations are uniformly spaced around the ring. Data frames are 256 bits and including 32 bits of overhead. The token is 8 bits long. Find the effective data rate. So we need to find out the effective data rate. So for finding effective data rate, we need to find out the total packet transmission time and also the token time. Okay. So what is the packet transmission time? So there is a 256 in a data frame. Okay. 256, in which rate it is sending? 10 Mbps. 10 Mbps means 10 into 10 power 6. So this will be 25.6 microseconds in the microseconds. Token time. Token is 8 bits long. It is 8 by 10 into 10 power 6 because 10 Mbps. So this is plus this transmission will occur in total length 1 kilometer long, because the token travels the total ring. Okay, so this is 1 kilometer per 50 stations. So and the propagation time is 200 seconds, microseconds, 200 meters per microsecond. Okay, so this will be equal to 0.8 plus 0.1. This is 0.9 microseconds. Okay, total time is 25.6 plus 0.9. It will be 26.5 will get total time. And the data rate, we have to exclude the frame overhead. So 256 minus 32, it is 224. Effective data rate is 224 bits. We could transfer at a rate of 26.5 microseconds. So it will be 8.5 Mbps. Option D is the right option.